Alright guys, now it's time to actually do the coding things. So here I'll provide this notebook for you. So simply what you have to do is simply go to the file and then upload a notebook and then simply drag and drop the notebook for building detection. Or maybe I need to choose the file and then choose it from download and then just upload it. Yeah, after uploading the file you will see the similar interface, all the things, all the materials inside the notebook. So before we proceed, I just want to let you know about the some of the basic setup in the Google Colab. So first of all, you need to go to the runtime and then you need to change the runtime type. So make sure you have selected GPU so that your processing capability, model training capacity will be a little bit faster than the normal one. And after that, make sure you already downloaded this data from Kaggle, and then now you are ready to go. And then make sure you have the similar structure of folder train and test, and inside train and test you have upload the dataset in this format, I mean the original format .tif file. And after that, the first step for this process is to import the necessary libraries. For this purpose, I'm going to import the globe, which is very helpful for selecting the number of files. And then of course numpy is needed, and matplotlib for plotting the figures, and PLI for simply working with image. And I am also importing some of the core things with the TensorFlow keras, which is model, and then this all convolution layer, input layer, max pooling layer, and dropout things. This all will be used in model builder. And you need to run this cell. If you have any difficulty running this cell, that means you might not have installed the TensorFlow and matplotlib. Make sure you already install these packages. So yeah, so after that we need to connect to our drive so that we can let's say play with our drive dataset. To do so, simply run this cell and then it will ask for permission, and then just you need to click on your account and then simply allow it. Okay, I think it's running now, it's done. So now my Google Drive is linked. So if you click on this option, and then now you will see the G Drive folder. If you did not see this option, then you probably need to refresh here, and then you can go to the drive. Now inside my drive I have all the dataset inside dl directory. So I'll simply copy this path, and then you need to replace this path with your own path. Yeah, and then run this cell. Okay, after that, our we have set the working directory and then connected to Google Drive and then imported the packages. Now it's time to pre-process the dataset. So to pre-process the dataset, we are already inside the building detection folder. So inside there there is two folder, train and test. So here I'm going to select the train folder and test, I mean train file and text file using globe package. And this sorted is very useful for sorting the our image and label, so that it will match with the corresponding image. I mean same let's say we have the one image with the 10 buildings, and then we'll need the exact same imagery label. So that's why I'm sorting the values, sorting the list. And simply you need to run this cell, so control enter. And then after that you'll see there are 70 train x file and then 30 text x file. That means we have 70 images for training and 30 for testing. Now it's time to convert the training imagery to the NumPy array. So to convert that, make sure first of all you have to create the NumPy array with zeros. For me, for the training set, we have 70 data set, and I know the height and width of image 128 by 128. And then since training image is RGB, that's why I am writing 3. And then for the max it's only one band, single band image. And now I am iterating the for loop for image in for each image in each max dataset. And then simply this enumerator is useful to print out the numbers, which number we are in. And then I am writing both things inside zip, since length of x train and train x and train y are same. That's why I am simply zipping it. And then here in this step I am simply opening the image, each image, and then I am converting it to the NumPy array, and then simply indexing this NumPy array to the my original this zero array. And same thing for max dataset. So here I open the max data and then converted it to the NumPy array. And for max data actually there were only 128 by 128 shape, because there is only one band, so last dimension is not there. That's why I reshape it into the 1. And then again I assign this NumPy array to the train yy variable. So if you want to check the simple how this image look like, so NumPy array look like, maybe you can print here and then see. Okay, or maybe just the for this maybe I'll print out np max and then shape, only the shape. Okay, so this is my image. I think it's 128 by 3 dimension, and this is my shape of the max image after reshaping it to the 128 1. So I'm simply removing these things and then maybe commenting these things for now, and then simply let me run this code. So it will simply assign all the it will simply change our images file to the actual NumPy array. It might take some time. So all right, now it's done. So we have to do the similar thing for the test dataset. So I'm simply going to run this cell. It's exactly the same, just the copy of above code. All right, it's done too. So now it's time to check the plot whether our train data set and training image and max image are perfectly matching or not. So let's check. Okay, so for this sample these are the building. It looks good, and maybe I can change this number to the 20. and then see the 20th image. Okay, now it looks good. So yeah, everything looks good, so maybe we can move forward to the model development now. So for this purpose, actually I'm going to use the unet model. Actually, unet model is very popular for the image segmentation. It's originally from the I think biometric some biomedical field. And then here what we are going to do is we have the input image with the 128 128 by 3 channels, and we are passing this image to the 128 by 128, and then with the filter size of 16 convolution layer, and then again we are passing it to the convolution layer with max pooling with the help of, I think we are using the dropout and max pooling. So after that, simply we are reducing the, I mean making it more denser, and after that we are simply upsampling it, and then making the flat image, the normal image. The output of our model will be 128 by 128 by 1. So this is the simple architecture of unit. And but for this case, actually I'm simply writing the very small model, not the heavy, not the this much deeper module. Actually for this text we have the initial input is 128 by 128, and then we are applying 32 filters, and then 64, and I think only the two means I think we are just here, and then we are just again start upsampling the things, not these below things, because whenever our model get denser, it will take more time to train our model. That's why I'm simply using the simpler version of unit. So these things after that in at the final, so I have connected this layer with the activation function of sigmoid. Since our output value are either 0 or 1, only two case binary classification case, that's why sigmoid works very wonderfully. And now in the model we have the input of x in, and then output with the this x out variable, just 0 or 1. And then we are compiling this model with mean square error loss function. There are large number of loss functions, predefined loss functions, as well as you can write your own loss function too, depending on your text case, what you are trying to solve the issue. And then for the optimizer, Adam is the very popular optimizer, so I'm simply applying it. And then if I write the model.summary, then I'll get all the summary in this way. Yeah, so I have convolution layer, and then I have dropout layer to solve the vanishing gradient issue. And yeah, here you the most important thing is we have trainable parameter of, I think, 409 1281 parameters. So it's not that much, so it will train much more faster than the deep unet model. Okay, now in this section we are going to train the model. So to train the model we have to write model.fit, and then our training data, training input, and matching output. And for the validation, actually I'm passing simply test data set, and then for now I'm simply trying it with the 100 epochs, batch size of 10, and then var was maybe I can write 1 to see the output. If you write 0, then it will do all the process internally, so you will not get any outputs here. So simply run it. So after that you will see the processing things as well. It's simply trying to run the 40 ports, and maybe yeah, it will take a little bit of much time, so maybe I'll simply stop, pause the recording, and then I'll resume it back whenever it gets ready. All right, now my training model training process is done. Actually, it's quite faster because I have only tested it with the hundred images with 100 reports, and then it's very small data set, and also our model is not that much denser. It's the simple light model. So now one thing you might have noticed is this loss value. So it's initially 0.2828, and it's gradually decreasing. That means it's good. That means our model is learning the things, and then it has some, I think, some improvement. So if you try to plot this loss and val loss function, val loss values, simply you can get these values from history loss, and then history val loss. And if you simply plot these things, so our model is training like this. So our accuracy is increasing, this loss is decreasing, means accuracy is increasing. So yeah, so now it's time to predict the building detection model, whether it's correct or wrong. So simply run this cell. So the first line here, what it is doing is it's trying to predict the our images on test dataset. And then now if I try to visualize the test dataset test value, and then the actual test value, so it will look like this. So it's not the perfect one, but of course if you have the large number of data, I mean the input images, and also if you have developed your own model and loss functions, and you tune the parameters like learning rate, and try to optimize the hyperparameter, then this accuracy will much more improved. But for now, yeah, it looks a little bit weird, but yeah, it's good. Maybe I can try for another image. Okay, yeah, this is our model prediction, and this is the actual scenario. All right, so another thing here is you might be wondering why this color, it has different multiple colors, not only the binary things. This is due to our prediction is between 0 and 1, so we just need to either say it 0 or 1. So to do so, maybe I can define the threshold value will be maybe for initially I can write 0.5, and then now uh, I have to say if our predicted value is greater than 0.5, then I can assign it 1. Otherwise I can assign it as simply 0. So if you try to print the predict dot shape, so it will be the total shape, I think 30 128 by 128 by 1. Now you can clearly distinguish whether our prediction is matching or not. It looks like, yeah, almost matching. So the first one is our predicted image, and then the second one is our original, I mean the actual max. So yeah, looks good. So these things you can definitely improve by using the different model or the different loss function and try to tune the hyperparameter. And also let's say if you have the large number of data, then this model will improve. Yeah, I think that's all about the building detection. So I hope you enjoyed it. I'll see you in next lecture.